Hey guys, here's that simple harmonic motion phase angle question I promised you. So first things first is, as good practice, it'd be a good idea to pause the video and try it for yourself. See if you get the right answers, which will be revealed as we go through this. And yeah, that's always the best way to learn physics, is try and, try, practice, repetition. A lot of practice. So like, just seeing someone solve problems is not going to help you. Well, it'll help, but it's not the full answer. So here we go. So first step is I'm going to break down the problem. So we look at it piece by piece. And so we see here we have a spring hanging from a ceiling. So I'm going to draw like the initial situation here, where we have just a spring dangling without a mass. And then it says we add a mass. And if we were to just add that mass, we'd sort of, I'm exaggerating the spring here, but it would hang something like that. Okay, so this is the string when it's unstretched, and this is the string when it's stretched. And then if we were to hit this mass, it would go up and down and up and down and up and down and up and down and up and down. Basically forever if we consider this an ideal situation, which is how you're going to consider it. And so what does the problem tell us? So this is what's going on in this problem. We don't know if it starts going up initially or it starts going down initially, but this is the motion that it's going to go through at some point. And so the first sentence tells us a mass hangs, vertical oscillation, 1.25 hertz. So that means there's 1.25 cycles every second. And a cycle is simply from one part on the curve going through an entire cycle to another part on the curve. So it's not when it finds itself again, it's when it does a complete wavelength. Okay, so that's a cycle is that distance right there. And so it says there are 1.25 cycles every second. That's what the 1.25 hertz is. And when the mass is at the highest point of the oscillation, the string is stretched by 4 centimeters. So what they're saying there is that so this is the highest point of the oscillation. And they said that this distance from here to here is 4 centimeters. So that's the distance from the unstretched spring to where it is here. They say that's 4 centimeters. And now the third sentence, a stopwatch is started during the motion, found the mass is 5 centimeters below. Okay, so that's going to talk about another situation that we'll get to eventually, but we don't need that for part A and for part B. So let's look at part A. So for part A, the angular frequency. Well, that's pretty easy. Omega, you'll have a formula. Omega is 2 pi f. And you simply plug it in and play. Okay, so I'm going to use my trusty little calculator here. 2 pi times 1.25. So 7.89 hertz. Okay, easy peasy. Okay, A's all set. So now let's look at number B. The extension of the spring when the mass is at equilibrium. Okay. Okay, now this part is a bit trickier because it doesn't seem to give us any information that we need. So, but let's look at some formulas that we know. We know omega, the angular frequency, is, for simple harmonic motion, is the square root of the spring constant over the mass of the spring. So we know that for simple harmonic motion. So we have this one formula we can work with. And what else do we know? Well, at the equilibrium position, I'm going to go back to our picture here. We have two forces. We have gravity pulling down, and we have the spring pulling it up. And we'll just call that Fk. So if we do if we analyze this free body diagram here, and we'll say up is positive, then we say that Fk minus Fg equals ma. And what's the acceleration? Well, we're gonna say that we're just sort of holding it stationary, or we just let it come to rest, and that's what happens at equilibrium. So at that point, at equilibrium, a goes to 0. So we can just rearrange this to have Fk equals Fg. And what are these forces? Well, the spring constant is, or the force from the spring is Kx, and the force of gravity is mg. So we have these two equations here. And with these two, we are equipped to solve this problem. This problem B here, because we're going to have some cancellations. So let's rearrange the red equation and rearrange the red equation, and we're going to solve for x. Okay, so let's rearrange our red equation, and that gives us x equals mg over k. And you see we have an m over k here, but here we have a k over m. So let's rearrange our green equation now to help these two equations agree. So we'll square both sides. We'll start with that. Omega squared equals k over m. And then let's multiply both sides by m, divide both sides by k, and divide both sides by omega squared. Basically flip this whole guy around. And so that's going to have m over k equal 1 over omega squared. So there we have this m over k here, and we have an m over k here. So we're going to replace, we're going to replace this m over k with what we have for m over k right here. So let's do that. So that's 1 over omega squared times g. That's what x equals. And so that's simple. We can figure that out now. We have the numbers for that. So let's do it. So 0.157 meters, which is equal to 15.7 centimeters. Okay, so we've done A and B now. Now let's move on to part C. So part C is asking for the amplitude of the motion. Well, from our picture, that makes sense now. So we have the 4 centimeters is what was given, and we figured out this 15.7 centimeters, and what distance is that? Well, that is the extension at equilibrium. So that is the distance from here that's the distance between those two, and we know that the distance from there to there is 4. So the resulting, or the only distance we're left with then, which is going to be the amplitude of the motion, is simply 15.7 minus 4. So we'll write that as amplitude equals 15.7 minus 4. These are all in centimeters. So that's simply 11.7 centimeters. Awesome. Okay, so we got our amplitude now. Now on to probably the most important one, the reason why I'm doing this, and that is the phase angle part. So I remember when I was in undergrad, I knew how to do these problems, but I skipped over this one. It had like special rules. I didn't really get it. You know, you're learning like so many topics at the same time. I just sort of left this one at the side. But yeah, I finally came back to learn it, and I'm going to share with you guys. So phase angle. Okay. So okay, so we know the equation. They give it to us. And this carves out the path that the particle takes in time. And so what this equation does for you is it tells you the position y as a function of time. So omega is a constant, a is a constant, phi is going to be a constant, that's the phase angle, and cos just oscillates between 1 and 0. So this is going to carve out this sine angle that or this sine curve that we see that the particle carves out here. And this is going to describe it once we get all these numbers right. And so what do we know? Well, we know A, we know omega, and we know one more thing from what they give us in the question, and that is we know that at 2 seconds the mass is 5 centimeters below equilibrium. So y at 2, or sorry, 0.2 is -5. Okay, so let's sub that in. So we're going to sub in for y, put -5. A we know is 11.7 cos. Omega we know is 7.89 t plus the phase angle we do not know. And actually we do know time, because time is 0.2 seconds, so 7.89, 0.2 plus the phase angle. Okay, so now it looks like we have an equation with simply one unknown, so we just solve for phi, right? Well, this is where it gets a bit tricky, and there's these rules. But actually we can ignore these rules, and there's one simple equation we need to know. But let's work this out right now. Okay, so this looks simple, but it's actually not. And so let's work through it anyway. And first I'll show you how we're gonna go through it, and then I'll show you why. So let's do the how first. So basically we put the cos by itself. So put -5 over 11.7. So I brought that 11.7 down. Cos of actually, this is a good opportunity for us to multiply out 7.89 times 0.2, so let's do that. Okay, 1.578 makes sense. Okay. Okay, so now we get to a point here where we do two things. We don't just take the cos inverse. We use the fact that cos of theta, actually let me put this in a different color. We use the fact here that cos of theta is equal to the cos of negative theta. So using that fact, we can do this equation twice, and we can get two separate answers. So first, let's do it for just the normal case that we see right in front of us. And we'll just put cos inverse of negative 0.427 equals, and so if I do cos inverse to both sides here, I get a cos inverse on that side, and then a cos inverse of cos is just simply what's inside. It's 1.578 plus phi. And then we ask our calculator, what's the cos inverse of 0.427? also known as the arc cos.